Here is a proof of Theorem 9. As you know, or as you might know, Theorems 9 through 12 are all constructions. I'll have a video for each of these 4 theorems that I'm posting on the Google Classroom, and you will be responsible for all 4 theorems. We'll be taking a quiz in which you will have to prove one of the theorems, but you won't know beforehand which one. So you have to learn all 4 because you may get any one of the theorems. I'm just going to make 4 quizzes and just mix them up at random and just pass them out at random, and you'll have to do the one that lands on your desk. And if you need to retake, you will have to do a different one than the one that you failed. So, all right, so here we go. Theorem 9 is a construction to bisect a given rectilinear angle. Rectilinear just means angle made with straight lines. And of course, so we have given this angle, angle BAC. Okay, you could just call it angle A, but I'm going to call it BAC because that's what Euclid does. And it is required that we bisect the angle. So we got to construct a line, okay, and that line is eventually going to be called AF, which is going to bisect angle BAC. All right? And of course, you have to use compass and straight edge. You can't just guess, oh, F is maybe right here in the middle somewhere. No, it has to be perfect, and it has to make these 2 angles, BAF and CAF, equal to each other in order for it to be a bisector. All right? So here are the steps of the construction. So step 1 is going to be choose a point D at random on AB. So I'm going to choose it right there. And then I'm going to cut off AC at point E so that AD and AE are equal to each other. So let's write all that out first, and then I'll do it. So we're going to choose point D at random on AB. And we're going to cut off AC at E so that AD and AE are equal to each other. And of course, the reason we can do that is Theorem 3, cutting off a longer line to equal a shorter one. And since they are both going to be the same distance from A, Theorem 3 for us means we just have to use our compass to find point E like that. There we go. So that's point E right there. And the next thing we do is we're going to join DE. Draw DE using postulate 1. I almost wrote theorem 1, sorry. Okay, so we're going to draw DE. And then we're going to do a theorem 1 on DE. We're going to draw equilateral triangle DE, let's call that third point F. That's a theorem 1. And so I'll just do that really quickly here. Remember, to do an equilateral triangle, we just open our compass to the length of the line we want the equilateral triangle side to be. And we just do 2 little arcs here.
Please report to Mrs. Munson's room. Got it.
All right, and that's going to be point F right there. So I'm going to just draw the lines here. That's part of theorem 1, is to draw the lines. So I don't have to say draw the lines, but okay. Now the last step of the construction is simply to draw AF, postulate 1, and that will be our bisector. There we go. I drew it past F. You don't have to do that. You can stop at F. All right. So I say that AF is a line that bisects this angle BAC. What does that mean? To bisect means to cut into two equal angles. So I'm going to call those angles angle 1 and angle 2. Again, I called them earlier BAF and CAF, but I'm just going to call them angle 1 and 2 because it's easier. But I don't expect you to just take my word for it. I'm going to prove it to you now. So every proof you should state what's given and what you need to prove. And what's given is the construction that I just did. So I won't repeat it. I'll just say the construction above. And I need to just prove that AF bisects angle BAC. Notice that this is identical to what I put up here that I wanted to construct. Okay? And that's also going to be identical to my last step of my proof. It's the bottom here. Okay? All right. So what do? How am I going to do that? I hinted before how we're going to do that. How will you prove AF is a bisector? Is you prove that angle 1 equals angle 2. And the way we're going to prove angle 1 is equal to angle 2 is we're going to prove two triangles congruent that have angle 1 and angle 2 as corresponding angles. Corresponding parts of congruent triangles are congruent. Therefore, if I can get these two triangles and prove them congruent, then I can just use CP/CTC to prove 1 is equal to 2. Do you see which triangles they are? Okay, a lot of beginners will say, well, I see them right here, Mr. Blackhawk, A, D, and whatever this point is. Well, Euclid doesn't name that point, and neither should you, because there is no way you're going to prove those two triangles congruent without proving another set of triangles congruent first. All right? There's just no way to do it. Okay? That's why let's just stay away from that point. No, in fact, it's actually going to be ADF and AEF that we're going to prove congruent. Okay? So we're going to start by saying we made AD equal to AE before, so we're just going to restate that right now. That was based on Theorem 3. We're also going to say that DF is equal to EF. And where does DF and EF come from? It came from over here, step 3, draw an equilateral triangle. Oops, I forgot to label it EQ. Okay, it has to be an equilateral triangle. DF can't be just any old triangle. And so we're going to say that that is because of the definition of an equilateral triangle. Definition of EQ triangle. All right? Click, click. All we need is one more click, and the locker opens. We can prove the triangle's congruent. The third click is that AF equals itself. The two triangles share the line AF, and since things that coincide are equal, AF is equal to AF. So that would be axiom 4. You could also just write reflexive, or just state the theorem I just stated. Things that coincide are equal. All right? Now, I just want to make the point that these 3 steps depend on things that we did over here in the construction. Therefore, it does not matter the order that you put the first 3 steps in. Order does not matter. So, however, you must have all 3 steps, click, 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 in order to open the locker or prove the triangle's congruent. So you can't say ADF and AEF triangles are congruent until you've said all 3 of these things, because it takes 3 sides, according to Theorem 8, to prove that triangles are congruent. Or it takes 2 sides and an included angle, but we don't have any angles congruent on these 2 triangles yet. So we're going to just use the sides instead. So ADF is congruent to AEF by the SSS. What always comes after the SSS? Why we'll open the locker, we take out treasures using corresponding parts of congruent triangles are congruent. And the treasure we want to take out is just these two angles. Angle 1 is an angle in triangle ADF, and the corresponding angle in triangle AEF is angle 2. So therefore, they are corresponding parts of congruent triangles, and they are congruent or equal. All right? And that proves what we wanted to prove. That proves that AF bisects angle BAC. And so that is by the definition of bisection. QE, remember what we say after a construction? We don't say QED, we say QEF, quod erat faciendum, which was the thing we needed to make or to do. We needed to bisect that angle. And so this just says we have done it. Notice again how this matches the original thing that we had to construct. It also matches what we wanted to prove. That's it. Onward to Theorem 10.